Okie dokie. So going on page 89, we are starting Unit 3. The overarching theme in Unit 3 is trig. You're probably not going to see how today relates to trig until later on, and that's okay. I like the way that this starts out. If you already know this stuff, then you can kind of see where we're going. And you won't see that, that's okay. Just trust me, hang on. It makes it easier to go through it like this anyway. But the name of this topic is periodic phenomena. All right, phenomena is a plural form of phenomenon, okay? And every time I hear the word phenomena, there's a song that plays in my head, and I don't want to be selfish and have the only one with this song going through my head the entire day. So I'm going to put the earworm in your brain too, so that it's playing over and over in your head, all right? Ready? So here we go. This is how much I love you. I'm not playing you the whole thing, but just some of it. Phenomena. That's what I hear. Phenomena. That's not what he's saying, but don't you hear it? Okay. Then he goes on and on. He's crazy. But y'all hear that? Phenomena. So I want that do. It should be playing in your head. Just because I don't want to have the only one that is playing through my head all day. So, phenomena. Think of the Muppets. All right. So let's talk about what a periodic phenomena means. We have a periodic relationship relating to the word period, which is the root word of that. It's a relationship between two variables when the output values demonstrate a repeating pattern over, and we've heard this phrase a bazillion times, successive equal length intervals. Everything's about successive equal length intervals, right? So the period of a periodic function is the length of the x value interval, basically, that it takes for the function to complete one cycle. All right? Now, sometimes the question to me, the wording is a little bit weird, like it'll say, what is the smallest possible period? So if you look at this function here, you can see, hopefully, that it repeats, right? And so when I want to figure out what the period is, I can really start anywhere, okay? Because there technically is not a beginning, because this is just two cycles of it that are drawn, and it goes on infinitely in both directions. But I could start here and go from -1 to 3, or I could start here and go from 1 to, 5? Right? And then think about it repeating there and so forth and so on. Because you can start anywhere. It doesn't have to be at a specific, it would be easiest to start at one of the actual points instead of like on one of the diagonals, but you could start it anywhere. But who's to say that the period here really isn't 8 and that this is the thing that repeats? So when it says the smallest possible or the least possible value for the period, that's when we would, and sometimes wherever you think the beginning is, works. A lot of times I'll start it at when x is 0 to make it easiest. I think this one's maybe a little bit easier. And I'm going from -1 to 3. So since I'm going from -1 to 3, that still is a distance of 4 units. Does that make sense? So the function f is periodic, and it says period with period 4, so we didn't have to figure it out. It told us, but that's what's happening there. A portion of the graph is shown above. Draw 2 additional periods. Now, before you do that, I know this is not a difficult task, but we need to kind of make sure that we get what's happening here. I know you get that it's repeating. It's not that I'm concerned with. It's that there's a couple different ways that you could repeat the drawing. But what I want you to see is happening is if I am looking at this part here as the part that is repeating, right? Or the part before it doesn't matter, it's the same thing, right? So then I have, when I look at this point here, this point, which I didn't really mean to mark, I'm going to take it and I'm going to move to the right 1, 2, 3, 4. It ends up here, which makes sense because that's where I should start, right? This point, I move it to the right 1, 2, 3, 4. Now, one way I can do the next one is just to say, oh, that's 1 away. But again, we're here, and then I move to the right 1, 2, 3, 4. Here, I move to the right 1, 2, 3, 4, and then I can draw that in. All right? And you can go ahead and draw the next one into because I know you can do this. It's not like you haven't done stuff like this before. But every single point is moving over 4. Right? You did translations geometrically, you probably did stuff in tessellations and things like that. It's the same concept. But that's going to help us, 1, 2, 3, 4, when we, 1, 2, 3, sorry, I can't count and think at the same, and speak at the same time, or think at the same time. It's going to help us when we try and do some of this stuff algebraically here in just a second. So there's the repeating 2 patterns. You're not going to be asked to draw that stuff a ton, but everybody good with that? So this is a periodic function. We would also be told things probably like, is this true for the domain of all real numbers, which means not only can we repeat it to the right, but we can also repeat it to the left. Okay? That's what makes it a periodic function. Now, let's look at this next one. It says a portion of the graph of the periodic function g is shown above. And here's where that wording comes in. What is the least possible value for the period of g? So, remember, I could start this anywhere. I could start here. If I start here, that it would repeat until I got to, or I mean, one cycle would end here, right? Or I could start here, and the cycle would end here. Or I could start here, and the cycle would end here. It doesn't matter, all right? I personally think that the easiest way to do it is if I start at x equals 0, figure out where it goes until it repeats, then I'm going from 0 to 5, and the answer would be 5, right? Now, I could have started at 0 at the one above it, but to me it was easier to start at -1, but you can start wherever you want, it doesn't matter. Okay, we all okay with that? So now we're going to be asked to find, we're using the period that we came up with and the function g in the graph to find the following values. Now, I could keep repeating this graph going to the right and to the left, but I don't want to do that because that's way too much work and we won't always have a graph. But instead, I want to use what I know about periodic functions to be able, and what the period actually is, to be able to figure out what else I could find besides g of 14. Because the y values are going to repeat. Y values repeating are fine. X values, not okay. I know the period is 5. When I have g of 14, how many 5s evenly go into 14? 2. Okay, so I can rewrite this as g of 4 plus 2 times 5. Right? Where 5 is the period. And I'm going to abbreviate period as PD, so we don't have to write it over and over again. Sometimes I'll abbreviate it just as P, but I want you to make sure you understand what's happening. So so if I go to 4, and then I go 5 down, and then 5 down again, all those y values should be the same, right? So this is the same as g of 4. What is g of 4? 7. How do you know that? It's on the graph, exactly. Right? That's g of 4. 4 is something I can actually find. It's right there. It's 7. Okay? So we're trying to get it to something that we can actually find. We okay with that? All right. Earbuds out, guys. Gavin, Adam. Let's go. Everybody else. Check it out. All right. G of 72. All right, so my period is 5. How many 5s evenly go into 72? 14. How many 10s go into 72? 7, which means 5s would be the 14, right? Okay. So this is going to be g of 2 plus 14 times 5. So this is the period. I definitely don't want to draw that until I get to 72, right? I don't need to because I understand how the periods work. So really this is just g of 2, which is what? 6. What questions you got? Alrighty. Now, g of negative 17. So some of the negatives we have to think through a little bit differently, but really this one we can kind of do almost exactly the same. How many 5s go evenly into negative 17? 3, okay? So and also one thing I want you to notice is that whenever I do this, this has to equal this. This equals this. So I got to make sure that when I'm doing this, that's going to equal it back up. So I can make this g of -2 minus 3 times 5. Because remember, I can go to the right or the left. So I can subtract the periods and go to the left. That's fine. -2 minus 3 times 5, this being the period, that would give me the -17 back, right? Which means this is really just g of -2. Is that something I can get off the graph? What is it? 7. All right. What questions you got? Uh-huh.
So the -2, the 2, and the 4, what does that mean?
Basically, yeah. You don't need to state that. You don't have to write this every single time. You need to write this, but I'm just doing that so we understand what the pieces are. On your notes, it's probably a good idea, just so you can remember what the heck's going on, but when you actually do it, you're fine. We good with that? All right. So this next one, this next set of stuff, we don't have a graph, we have a table. So I want h of -2. -2 is not an option for me up there. It tells me that the period is 5 again. The values of h are shown. See if you can rewrite h of -2 and figure out what that is. I'll give you a second. How can I use 5 and something in my table to end up with -2? Anybody? I can make this h of you're on the right track. Not -3, but if I use 3 plus -5 or just -5, which is fine either way. And then this is the period, and I only needed one of them, right? So that means this is the same as h of 3, which is 0. Okay, everybody okay with that? All right, see if you can do B. And is there more than one way we could come up with these? Absolutely. So you don't have to get stuck in one, but I'm just kind of going with probably what most people would think about, unless you give me a different one to look at. All right, h of 6. Who wants to tell me how to rewrite this one? 1 plus 5. Good. 1 plus 5, because that's the period. Is that the only way to do it? No. Did anybody have anything different? Okay, that's the way I would have done it too. I think that's the easiest. Then h of 1 equals -2. Okay. Everybody okay with that? All right, good deal. What about h of 9? Does that make it any more difficult? No, just one more step. So let me give you a second to think through that one. How can I rewrite the 9? 4 plus 5. Okay, good. 4 plus 5. That's the period. So that means that's the same as h of 4 H of 4 is something I can figure out. That's 3. So then I have H of 3. Do I need to rewrite that? I don't, because it's up there, right? If it wasn't up there, I'd need to rewrite it, but I don't need to rewrite it. Everybody okay with that? Any questions? Just by the nature of the values. Like, I only needed to add 1 5. I didn't need to add 2 5s. That's why we're multiplying on the last one. Does that make sense? Yeah, so if this was 14 instead, then I'd have 4 plus 2 times 5. That's a good question. And it just happened that all the last ones I was multiplying and this one I'm not. Okay, good question. Anything else? All right, so let's look at D. H of 5k minus 3, where k is an integer. So how do you think I can rewrite this? This would be the same as h of what? Don't overthink it. It's actually super easy. What's the period? 5. So 5 times k, k could be any integer, right? It can be 1, 2, so it could be 5 or 10 or 15 or negative 5 or whatever. So does this really affect the answer? No. So it's really just h of negative 3. Right? Now, that one I need to rewrite. So let me give you a second to think about that, how you would do that one. Anybody have any ideas? Do what? 2 minus 5? Now 2 minus 5, will that work? Because 2 is not, so 2 minus 5 gives me negative 3. So it works, but 2 is not up there. So good thought though, you're on the right track. Negative 3 plus 2 times 5. That's what I heard. Well, if I do negative 3 plus 2 times 5, does this add back up to that? No, but you're on the right track. See, you're on the right track. I know what you're trying to do. Okay, it's 7 minus, yeah. Now with the negative ones, you have to think just a little bit harder. Yeah, sometimes. Sometimes it works out nicely, like with that negative 17, it worked out just fine. This one was a little bit different. I need a number that's up here, right? So if I do 7 minus what? 2 times 5. Good thoughts, though, guys. Your brains are on the right track for sure. So this is the period. So now I can ignore that, and I just want h of 7, which is 2. Okay. What questions you got? Anything? All right. Let's look at the next part. It is useful to have notation, really for anything, to model this phenomena. A periodic function starts with a basic pattern and translates the pattern, and then mark out this word translate because it doesn't make any sense, repeatedly over its domain. As a result, we are able to consider a periodic function as a horizontal translation of itself. Right? And just, if I just take the function going from negative infinity to infinity, and if my period was 4, whatever, if I move it to the right or to the left 4, it should look exactly the same. Kind of think about picking it up out of something that's it's molded into, and you can shift it over, and then it can plop back down to where it went, right? Just kind of fits right in the groove. All right. So in example 4, the period of h was 5, meaning that we could translate the graph horizontally 5 units and end up with the same graph. This means function h satisfies the following equations for all values of x. So h of x is going to equal h of x minus 5. That's basically what was happening when we were finding all those values, right? The 5 becomes irrelevant because you're going to have the same values. It's also equal to h of x plus 5, right? It's also equal to h of x minus 2 times 5, and so forth and so on. Okay? But this is the kind of the main thing we want to think about. Just means that your period is 5 and you can translate it. Okay? Everybody okay with all that so far? All right. Let's look at example 5. So we have the graph of f is periodic with domain of all real numbers, meaning we don't see the whole thing, but it goes on forever in either direction. 2 full periods of f are shown. Find all input values of f that yield an output value of 1. So the first thing I think I want is the actual period. So what do you think the period is for this function? I heard 5 and 4. 4. Good, because we're starting at 1 and we're going to 5. Or I could start at 2 and go to 6. Remember, it doesn't matter. But either way, the period is 4. Okay? I want an output value of 1. Well, that happens when x is 2. So I know that f of 2 is equal to 1. If the period is 4, that means f of 6 is also 1. F of 10, f of 14, and so forth and so on. So I know that f of 2 plus 4 times k, where 4 is the period, is going to have to equal 1. And k is an integer, so it can be negative. That's why you can put plus or minus. It doesn't matter which one you put, but you don't have to put them both. And then, so since it says find all input values, I wrote it like this. That implies that. But I would say that x is equal to 2 plus 4k. And again, that's basically what we were doing with all those where we were just straight up finding values. Same concept. What questions you got? Okay. This is also going on page 89 when we are done. Lots of words. This is an FRQ model, not drawn to scale. Most things are not, but especially with all these words and a picture, as I start reading, because I definitely don't want to have to read this thing more times than I need to, I'm going to start labeling, if I can, as I'm reading. So it says, the figure above shows a large clock mounted on a vertical wall. Check, it's there already, I didn't have to draw it. The clock has an 8-inch long moving minute hand. So this is the minute hand right here, and this is 8 inches. Okay. The center of the clock is 120 inches directly above the floor. Here's the center of the clock. This right here is 120 inches. At time t equals 0 minutes, the minute hand is pointed directly up at 12. However, the clock is not working properly, and the minute hand is moving twice as fast as it should. Thus, the next time the minute hand points directly up at 12, it's at t equals 30 minutes. As the minute hand moves, the distance between the end point of the minute hand and the floor periodically decreases and increases. So here's what this means. Here's the end of the minute hand, right? As we go along, the distance between here and the floor, it gets less, and then it gets, I'm sorry, let me just put that differently. It decreases, and then it increases, and then it decreases, and then it increases, right? Just keep going around the distance from the floor. All right, so before I go any farther, I've got t equals 0 minutes, and I've got t equals 30 minutes. Now, I don't know what distance I'm actually looking for yet because I haven't read that far, but before we read any farther and get anything else in our brain, I want you to tell me how these two y values would be related to each other. At 0 minutes and at 30 minutes. They're both at 12. Okay, so they're both, I'm here at 0, I go around, and I'm here. So what would have to be true about these y values? They're the same. Okay, so we know that they're the same. Now let's see what we're actually looking for here. It says the periodic function h models the distance, oh, I didn't mean to mark it out, I was trying to underline it, models the distance in inches between the endpoint of the minute hand from the floor and the floor as a function of time. So I'm looking for the endpoint of the minute hand all the way to the floor. So at 0 minutes, what is that distance? 128. At 30 minutes, what is that distance? 128. Now, again, I still haven't even read the rest of the question, but I want to make sure we're understanding what's going on here. So if this is 0 minutes and then this is 30 minutes, this is how many minutes? 15. So at 15 minutes, what is the distance from the floor? 1 what? 12. Good. Everybody with me on all that? Okay. So now, let me scroll some. Says the graph of H and its dashed line, dashed midline. So midline is a term that you are not familiar with yet, and that is okay, right? We're going to get there, but it's just the dash, that's a midline. That's all you need. That's in the middle, right? For 2 full cycles is shown. All right, so the other ones that we had, they were very boxy type graphs because they were with line segments. This is with a curve. But I can see if I start here, I'm going to go through 1 full cycle till I get to here, and then go through another one, and that gives me 2 full cycles. Thank you. All right. So I got 2 full cycles there, right? So 5 points F, G, J, K, and P are labeled on the graph. No scale is indicated and no axes are presented, which means I don't know what, again, since I don't know what the scale is, and I'm not saying that any one of these 3 is the x-axis. That's what it's getting at. They're there just so you understand the graph and how things work. But if these points represent the distance from the floor, when is the distance from the floor the most? When it's at 12, and so when it's at 12, right? And that's at 0 and 30 minutes, right? And then on this graph, when is it the most? F and P. So that means this would have to be at 0, 128. So what is that? 128 and 30, 128. Now, I can write bigger than you can, so we might want to also write these out over here. F, G, J, K. But I like to have them also labeled on here because we can make more sense of it. 0, 128, and P is at 0, 128. Okay. Everybody okay with those? Yes? Oh, it is 30. Jeez. Thank you. That's what I wrote right there. I didn't write it right there. We all good so far? So this is actually a graph of a trig function, and you're not expected to know that yet. Not expected to know that at this point. Totally fine. We're going to get there. But one thing that is true about our trig graphs that is not necessarily true about the other ones we looked at today is that everything that we do is always going to be half, 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 and that makes everything a whole lot easier. So between these two is definitely halfway, which we already talked about, right? So halfway between 0 and 30 is 15, and that's when it's closest to the ground. And what is the y value here? 112. Okay, and so that's J. This is at 15, 112. All right, and so then I'm going to draw another clock. That's this one. We already talked about this one. And so since everything is half, 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 this is halfway in between. So half between 0 and 15, we can use 7.5. But I'm going to tell you on some of the other ones that I give you with this, you're probably going to want to leave them as fractions just because getting the decimals is going to be a nightmare and it would not be a calculator question. Okay, but here I think 7.5 is easy enough. If it's simple like that, that's fine. But I think you will find on some of them, leaving it as a fraction will be way easier. So 7.5, okay, and that would be halfway here and here. So then what would the distance from the ground be? 120. So the distance from the ground at K is 120. What would the time be? 22.5. So G is at 7.5, 120, and K is at 22.5, 120. Now, let me make something very clear. the first point that we have doesn't always have to be your 0. Or the first point that you have isn't necessarily always the highest, right? Technically, I don't know, since I don't know where the axes are, this really could be 0, 128. Sorry. Or maybe they said that at 0 minutes we're here. If they did that, then I'd be starting here, right? So you got to make sure that you understand where you're starting, when is the greatest and least, and make sure you get those in the right spots. Everybody okay with all that so far? Okay. So then it says, refer to the graph in part A. The t-coordinate of G is T1 and J is T2. On this interval from T1 to T2, that means from G to J, this right here, which of the following is true about H? So there's two things we're looking at. And so let's just look at positive and negative first. Is H positive or negative on that interval? Positive. These are my H values, right? My function is function H, so it's T, H of T. So this is the time, this is H of T. The distance is positive, right? So it's positive, so I can knock both of those out. Because nobody said that the midline was the x-axis, right? All right, and then is the function increasing or decreasing? Decreasing, right? Because both of those were about H itself. We all good with that? All right, so then the second part asks about, it says to describe how the rate of change of H is changing over the interval. So what is helpful to have when we're talking about rate of change most of the time? The concavity, and how do we know how to relate the concavity? What can we write out? Fun chart, exactly. So here's the fun chart. And this is R for rates of change. I know I've changed that on you a few times. Now, here's something that I know. We've already said it's decreasing. So since the function is decreasing, then that makes the rate of change negative. Is that what this is asking? No, it says how is it changing, meaning is it increasing or decreasing? So that means for the function, I need to talk about the function. I can't say because I run my pencil along it and that type of thing. I have to actually talk about what I have. Is the function concave up or down right there? Up. So since it's concave up, my rate is increasing. Okay? So then we go to write that out, and we can say, just getting the words from the question, the rate of change of H is increasing over T1, T2 because H is concave up on that interval. And we want to stay on that interval because it's not concave up the whole time, right? You know, make sure that we're expressing that we understand that and that it's concave up on that interval. And that comes from your fun chart, okay? What questions do you have? Anything? We all good? All right, I will take that as a yes.